introduction to geometry, differential geometry. And the main goal is not to make people interested in differential geometry as its own story, but to introduce the PDEs of differential geometry as fast as possible. Okay. But you have to start someplace. So first we'll start with the ODEs of differential geometry and then move to the PDEs. And the lectures, the beginning material is taken from Frank Morgan's very nice book, and I recommend it highly. I also recommend inviting Frank Morgan to KAIST sometime. He's one of the world's greatest expositors of mathematics, and a very nice guy. Okay, so first let's start off with, as I said, to get to the ODEs of differential geometry before the PDEs. And I don't know anybody's background, but I'll assume almost nothing except calculus, no analysis, just how to differentiate. So, and now from the, I guess I can't get in this, so I'll work from left to right. Okay, and if I can see my own handwriting. So the first section, and the notes you can get on the web, of course. So you don't have to copy anything. It's all on the web page. So the first topic is curves in Rn, and so let's let x of t be a parametrized curve in Rn. Okay, and from Pythagoras we know how to find arc length, which is if x as written component-wise x1 through xn, then our old friend Pythagoras tells us how to find arc length along a curve. Okay, so, and we also know how to find the velocity, which is the rate of change with respect to the parameter t, or everyday life, how to find the velocity of the chalk going up and down is I know its position, x of t, and then I differentiate with respect to t, and I can find its velocity. And I'll sometimes use dot notation interchangeably. Okay, then of course the unit tangent is and I'll denote that by a capital T with an underline because it's a vector. So the unit tangent is just the velocity vector is of course tangent to the motion. So here's x of t. That's the velocity vector, and it's tangent to the motion. And if I normalize it, I make it a unit vector. Okay. And what else? Then we see, of course, that formally it's dividing through by dt, but you know what I mean. Again, Pythagoras says that. Okay, but that's just the magnitude of v squared, so ds dt equals the magnitude of v. So the rate of change of the arc length is just given by the magnitude of the velocity vector. Okay, that was very nice. So now we know about first derivatives, so we move on to the next story, which is second derivatives. And we introduce the concept of curvature. Now the whole subject, historically, grows out of an outgrowth of the concept of being able to define curvature. because that's what makes things interesting. So we know from whenever you took the first semester of calculus, curvature is introduced right at the beginning. Okay, and then we give the students some exercises to find the curvature, and then we forget about it. Whereas in real life mathematics, curvature is a crucial role, and we definitely do not forget about it, because computations, either in abstract geometry, all rely on a concept of curvature, whatever that means. And then because Einstein based his general theory of relativity based on the curvature of space-time, the curvature is the fundamental formula, the fundamental ingredient in Einstein's equations for general relativity, which are extremely simple. Very hard to solve, but extremely simple to write down. Okay. So a curvature first, we do the curvature vector, and then, so curvature is the rate of change of the unit tangent with respect to arc length. Okay, so let's compute it. So if I can, so let's do the computation. So what's the curvature vector? It's the rate of change of the unit tangent with respect to arc length. So there it is, mathematically written out. Okay, and then I use the chain rule just as a standard exercise. So this is dt dt, so I have to put the s dt in the denominator. Okay. But the s dt is the velocity magnitude. So it's the rate of change of the tangent vector with respect to time divided by the velocity. Okay. Also, since capital T is a unit vector, we know it's in a product, Euclidean dot product. With respect to itself has to be 1. So we made it a unit vector. So if I differentiate this with respect to time, then the left-hand side is the ddt of that one times this one plus this one times the root of that one. But since it's a scalar, it's exactly the same. So this just says that ddt dt dotted with t of t. It's actually twice, but who cares? Because the right-hand side is 0. So divide through by 2. But this is just the kappa times v, right? So this is kappa, the curvature vector times the scalar v, right, dotted with the tangent vector. So if the thing is actually moving in the space curve, it's not just a point. Okay, then this guy is not 0. So it says the curvature vector is orthogonal. So the curvature vector, okay, is orthogonal to the tangent vector, so that the kappa is a constant of proportionality times the normal vector. And that constant of proportionality is the scalar curvature. So there was a curvature vector and a curvature scalar, and the one we always ask the students to compute. Of course, the magnitudes are the same, because the n is the unit normal. So of course, kappa, the magnitude of the scalar, the absolute value, I'll use the same notation. Okay. So the absolute value of the scalar is equal to the magnitude. Here. And I used two lines to means two different things, but you know what I mean. Okay. So this is taking the, I should use double lines, but it's not get too confusing. Okay. The magnitude of the vector. So what does it mean? If you know the vector curvature, take its magnitude, and you'll get the scalar curvature plus or minus a sign. And the sign, well, really, does it really make any difference? Because all it means is which way you took the normal. Did you take it one way or the reverse? And does it really make any difference? The answer is, as long as you're consistent, it doesn't make any difference. So the magnitude is the guy that we're interested. Okay, so that finishes. Oh yeah, so let's see, so well, that's enough. Okay, now I wanted to find the curvature in terms of second derivatives, but let's do that again, and then I'll do a picture. Let's see. I can erase here. Okay, so I'll rewrite the formula again. So the SDT we said was the magnitude of V, and the XDS we said was T. Let's see, did I do this? The XDS is the XDT, right? The TDS, right? Okay. Which was the XDT, which is the XDT, the TDS, sorry, or the XDT over the SDT. Right? But the XDT is V. And the SDT we said was the magnitude of V. So if I did, so the XDS is just the, it's in the direction of the tangent. In fact, it's the unit tangent. So if I differentiate one more time, I get the second derivative of x with respect to s is the first derivative of t with respect to s. But the first derivative of t with respect to s is exactly how I define the curvature. So we have this nice formula. You can erase the middle, that this guy equals that guy. So another way to define the curvature vector is the second derivative of the space curve with respect to arc length. Okay, so let's do an example, but it's a little tedious, but let's do the one that everybody knows. So that's a curve in space. Let's just do the curve in the plane. So here's t, and here's x. So this is the graph of, so this is x equals f of t. So it's x. So this is the graph t f of t. Okay, so that's our vector. So as so as t goes along, I compute f of t and I draw the line. So let's just start the exercise. It's very boring, but anyways. So what's the x dt? It's 1 over there, f prime of t. Okay? Just to work it out once. Okay, so what's then I have to compute dx ds. So what's dx ds? Oh, what's the s? Oh, the s, of course, from Pythagoras is squared is 1 plus f prime of t squared times dt squared. So that's the ds dt, or if you wanted to do it that way, okay, is 1 plus f prime of t squared square root. Okay, so let's compute the x ds. First derivative, well, it's 1 plus, it's the vector 1f of prime t, but then I have to, so it's the x dt, and then I have to divide through by the s dt, the scalar, but I just computed the s dt, it's the square root of 1 plus f prime of t squared. So now I know dx ds in the simple example. Now I have to do one more computation. I have to take one more derivative. So let's see if I can do that. So I have to take this guy ds, which means this guy dt times dt ds. But dt ds is upstairs is the same as ds dt downstairs. And the s dt downstairs I just computed is 1 plus the square root of f prime squared. Okay, now that takes a little length, so I don't bore you by telling you things you already know. So if I compute that, and I'll get to after a bit of boring computation, you get to f double prime of t 1 plus f prime of t squared to the minus 2 power, if I have that, I can see correctly, minus f prime of t comma 1. So that's the curvature vector. So what's the curvature scalar? Well, you have to take the magnitude of the vector. Don't worry about the normal. So the magnitude of the vector is 1 squared, which is 1, plus f prime squared. Then take the square root. So you get in the denominator f double prime 1 plus f prime squared square root. So this will be the curvature scalar plus or minus. Right? And then I had this guy in the denominator. But you do a cancellation, and I'll use the eraser. Or maybe I'll leave it. So it's f double prime in the denominator, and 1 plus f prime squared to the 3/2 in the denominator. So that's the formula that everybody has seen in first weeks of whatever time you took calculus, high school or some other place. And of course the reason for the 3/2 is just to confuse the students, but anyways, but you see it makes sense. But if you really think about it, does it really make any difference? And the answer is, not really, because if you picked a point, you can always reorient the curve such that f prime is 0. You can't do it in general, of course, but at a point where f prime is 0, and then you see, oh, really the curvature is like the second derivative if you just reorient the graph correctly. So this is the usual calculus formula. So before I move on to surfaces, let me ask the question. Okay, you can. So I'm going to draw the same picture, but only bigger. Okay. It's not a test, so I'll. Okay. There's a curve, and I give you a point, any point you want. Okay. Point there. And I ask, how experimentally could you find the curvature? Okay, I don't tell you what f of t is, because that's cheating. Okay, I don't tell you f of t, all I draw is a picture. How can you find the curvature? Okay, well, we know the curvature of a circle, it's an easy exercise, is 1 over the radius. So if we have a circle of radius a, okay, so the curvature is 1 over a. Okay. I won't do this in every book, but you can just use this formula. Okay, so the curvature is 1 over a. Okay, so if the circles make the circle very big, then it looks like the curvature is 0. And if you think about it, that's what people thought before Columbus. Right? They walked along, said, looks flat, curvature is 0, okay, the world goes on forever, Earth goes on forever, Earth is flat. Okay? And A is infinity, cap equals 0. Then Columbus traveled, goes around, okay. Then, of course, the Magellan circumnavigated the globe. Okay. And they say, okay, not flat, so there is some curvature. Then you can ask the same thing about the universe. Flat or not flat? Is it finite? Okay. And if it's finite, what's the curvature? So, interesting. But going back to this question. Okay, so we know that the curvature of the circle is 1 over a. So the answer, okay, it's not a quiz as I said, is find the circle that fits the second order. So find a circle that touches to second order. What does second order means? The first derivative and the second derivative agree at that point. Here's the point P. So in English, okay, The word they use in the calculus books is osculating circle. Okay, which is I think must be in every calculus book ever written. Okay, is the osculating circle. It tells the students to find the osculating circle. Okay, it's an exercise. If I give you the curve, find the p. But this says the reverse. Okay, in the calculus books it tells the students, given the curve, find the osculating circle. It's an exercise because it says, oh, what do we force the students to do? Okay. Here we tell them, what does it mean? So we give them the curve t equals some function of t. T plus 3t cubed plus 14t squared, or who knows what. We give them the point at t equals 1, graph the curve, then what's their job? The job of the student is to find the curvature. From the curvature, find the inverse of the curvature, which is the radius of the osculating circle, and then just find the graph of this circle, okay, because that means you're given a point on the circumference and the radius, you find the center, and then you write the equation for the circle. Okay, extremely boring exercise, but first year. But the other way is a little more interesting. It says, how can you find the curvature, okay, with no computation? It says, start drawing circles. Maybe in the olden days, okay, before computers, you would use a compass and swing the arc around, and you could just play with it till you touched. These days with the computer, you could make the computer run around till you find the one that touches the best touch. Okay, it may not be perfect if you did it by hand, but it would be close. Then you find the radius of that circle, and then 1 over the radius is the curvature. So what's the point? The point is, there is a way to think about curvature independent of the formulas. That I think, even though the exercise in the books is trivial and it's just a homework assignment, there's something deep there, and I think. So the oscillating circle is important because it gives a way not to understand curvature without formulas, geometrically, truly geometrically. No formulas. Okay. And why do I mention it today? Because the next topic, I turn the page, is surfaces. And now I give you a surface, and the question is, what's the concept of curvature that we can think about without formulas? And that's not so obvious. Yeah. So I'll erase, and next half hour it'll be the surface. So we finished space curves, at least for now. So let's do surfaces. So the theory of surfaces was invented by Gauss. And this, I think, is the part, if I'm not mistaken, that is not in the usual calculus book. So we finished the beginning stuff. But needless to say, so it's Gauss's theory of surfaces. So the next section, which I guess is called 2, and it's surfaces in R3. Okay, so here's the surface in R3. A piece of paper is a surface in R3. So it's a two-dimensional surface, and it lies in 3 dimensions. It's no surprise that the abstract ideas for the theory of surfaces in two-dimensional surfaces in R3 became an important role not just in Gauss's theory of geometry, but in the 19th century, because people were trying to develop shell theory, that is, the behavior of thin bodies, like a shell, like even the shell of an egg shell, but all sorts of structures. It's much more convenient, instead of thinking of this structure as even if it's thin, it's much more convenient mathematically to think that it's so thin that we can treat it as infinitesimally thin and just as a lower dimensional object. Just like all these mathematical abstractions, it's a limiting process, and if the limiting process didn't make things simpler, it wouldn't be a good idea. But the fact is that the limiting process changes the problems from more complicated to less complicated. So engineers and mathematicians, applied mathematicians in the 19th century, could develop the theory of shells very nicely based on geometric ideas. So if you take a book on elasticity, for example, it's not by Love, the Elasticity, which is a paperback, old book, Elasticity. And what's at the end of the book, the last chapters are devoted to shell theory, and what do they have in the shell theory? Geometry. Okay, so let's do surfaces in R3. Okay, so of course that was due to Gauss. Developed the theory of surfaces. So a little history as I know it. So Gauss lived about 1830s, developed these ideas. Okay, and the next issue was, if we could understand it in 3 dimensions, what about arbitrary dimensions? And what's the essence of, how can the ideas that we develop in 3 dimensions be even extended to higher dimensional surfaces, which we may or may not be able to think about, or even higher dimensional guys, whatever they mean, as long as we have a concept of distance. Okay, and that's why, so this was Gauss's theory of surfaces, but then generalized by Riemann in his PhD thesis. So it's quite impressive what somebody can do in their PhD thesis. Okay, and that's led to Riemannian geometry. Riemann, and hence we had Riemannian geometry. Okay, so that was Gauss led to Riemann, led to Riemannian geometry, but then, as I said, then Einstein was able to use the tools. He didn't improve on the geometry, but he used the ideas, and then Einstein came up with general relativity. I think 1916, plus or minus, it was 1914, something like that. Okay. I can look up the date when the paper was published. So, and so these things play a role to this day. Okay, so let's draw the surface. Not that so there's the surface, and usually we would make the letters X, Y, Z, but it's not convenient. I'll start with X, Y, Z, but that's of course not a convenient. So let's assume we have a point P on the surface. So if a point P is on the surface, that means it has coordinates. If I think of this surface as lying above the XY plane, as usually we do in calculus, then it would be, P would have coordinate X, Y, and then Z of XY. So that would be, okay. And then we can make tangents to the surface. So you can make a tangent plane Okay. So, and the notation, I don't want to get into all this fancy notation, but a standard one. So, the tangent at the point P of the surface S, okay, exactly what it means, is called the tangent space. Which is the space set of all vectors tangent to S at P. So how do we figure out, so what do we do about curvature? And what do we mean by curvature? Well, just like in everything in mathematics and in life, as I teach my wife after all these years of marriage, how do we do life? How do you go along in life? And the answer is you reduce it to the previously solved problem. If you knew how to walk here yesterday, you know how to get here today. Life gets hard when we can't reduce it to the previously solved problem. But that's more or less how we live our lives. We try to reduce things to the previously solved problem. So what do? So I take the curve, okay, I slice it, slice, slice, slice. Every time I take a slice, I get a curve in the plane, in the surface, and I know how to take the curvature of the curve. So we take slices. Okay. Okay, and make, which implies we have curves. So for each slice we have a curve, so for each curve we have curvature. Okay. So let's take a point P. Okay, and let's draw the graph a little. So now we take a normal to the curve, and I have a better picture here. So let me draw this picture, because it's okay. So here I have put the three coordinate axes. Now I'm picking a point P on the curve. Let's move the point P to the origin. Makes life too complicated. It won't change the curvature, should have nothing to do with the choice of coordinates. So let's move the point P to the origin. Okay. Furthermore, okay, so it has a normal, right? Use n for the unit normal. So n is the unit normal. Okay. And here's the tangent plane. Okay. So I'm going to take point P, move it to the origin, and then rotate this so that the tangent plane, so I'm going to translate and rotate. If you take this and translate and rotate, can't change the, whatever concept of curvature or geometric ideas, can't make any difference. So translate, rotate. So now the normal is going this way, and I picked the case something like that just because it's easy to draw the picture. So I made it look like a parabola of revolution, but it's just to draw the picture nicely. Okay, so now this is what the surface looks like. I put the tangent plane here. The point P has now been moved to the origin, and now I can start to take slices. So let's take a slice. So we'll take a slice in the V direction. This V, nothing to do with the old V, because now we're in 2D. It's a two-dimensional surface. Okay, so we take a line in the V direction, so I'm taking a plane, and now I have the colored chalk. So the plane looks like that. So it intersects, the plane intersects the surface, and the intersection is here, someplace. I don't know. I should use another color. I'll make pink over it. And there it is. So there it is. And if I took a plane and cut here, I'd get a curve. So, okay, so now I have the curve. So that's the curve. So now I can find for that curve, of course, I can find this. The curvature vector, which must lie in the direction of the normal to the curve. Okay, so now what happens? You'd say, that's very nice, but it still didn't give, because every V will give a new curvature. So every V give a kappa. So what do? Work your way around through all the V's. Okay? That means you're going around the unit circle. Okay? You work your way around through all the V's. You'll get a biggest one and a smallest one. Let's take the biggest one, call it max, and the smallest. Min. So by taking the extremal, now I have something that's very well defined. Independent of V, because I took the extremum over all V's. So the largest and smallest ones, okay, I don't know. It doesn't make any difference, call one K1, the other one K2, if I can remember. So the largest one will occur for some V1, and the smallest one will occur for some V2. So there's a V1 vector and a V2 vector. So these are called the principal curvatures, AL curvatures. And these are the principal directions. So the principal curvatures and the principal directions. Okay. Now it said is in the anything else? I'm going to do the computation. Okay, before I do I wanted to do the computation, because it said in the notes the principal directions are orthogonal. And then Youngjung typed in Y. So let's do the computation, because it's useful. Okay, so I'll do that, and then I'll finish up maybe. So I'm going to erase here, we don't need that, leave that up, and let's find it's a nice calculus exercise. So maybe you can. So let's write the plane. Remember, this is a plane here, right? So I'm going to find the curvatures as a function of the angle theta when I run around the plane. So you can either use, so I chose v equals cosine theta minus sine theta. The minus plus, it does, as long as you're consistent. So that gives you points on the unit circle as you run around the theta. So there's my vector v. So this is a unit vector. So we can write that. Okay, then what's the plane? And the plane is sine theta x plus cosine theta y. And let's just check, okay, because to make sure there's no mistake, how do we find the normal to a plane? Okay, it's the gradient. What's the gradient? It's sine cosine. So if this is correct, then this one, sine cosine dotted with the v, should be 0 because the normal to the plane, this way, should be orthogonal to v. And it's true, right? So sine cosine minus sine cosine. And we get 0. Okay, so that's no mistake so far. Okay, so the plane intersects the so the plane intersects the surface. Okay, so that's the plane intersects the surface. And what's the surface look like? Remember, the surface had points x, y, f of x, y. So this is the formula coordinate the surface. Looks like x, y, f of x, y. But if that means if I have to get rid of either the x or the y, I'll get rid of the y. So the intersection means wherever I see y, I have to use the formula. So if I don't make a mistake, dividing through by y gives me tangent theta, and then move it to the other side is minus tangent theta times x. Now I substitute in. So that means the intersection, which is x, y, which is minus tangent theta times x, times f of x tangent theta times x. Now I have the surface where the angle is theta. So the angle is theta. That's x, y, z. And now we can find the curvature. So I have to do the bit of a computation. Okay, so I'll write it. You can work it out if you want. Let's just do one. So, for example, okay, how do I find? So I have to find. This is what I called before vector x. It's the point on the curve. And we had to differentiate it twice with respect to s. So first I have to find the x dt. Okay. Any parametrization. Okay. This time my parametrization, it's a little, so this is vector x of t, but it's parametrized by little x, because as little x moves, I'm getting the points on the curve. So I really should write little x equals t, but that gets a little confusing. So I have to differentiate this one once with respect to little x, and then twice. So let's do once, so we get 1 minus tan theta. And now this one, you have to use the chain rule. So it's f sub, means partial derivative, evaluated at x tangent theta, right? Plus chain rule on the other one, evaluated at tangent theta times tangent theta. Now I have to rewrite it, do one more computation. So I now know the x, so I know its magnitude. Which before we called the velocity, but anyways. So the magnitude is, you have to take the sum of the squared, so it's 1 squared plus tangent theta squared plus f sub x, I won't, plus f sub y, this guy squared, and then take the square root. Okay, so that's the magnitude, the x dt. So that means this one you can put together. 1 plus tangent squared is secant squared. Okay, so now we have to find, so this tells me that t is this vector okay. That's the velocity vector divided by its magnitude. Okay. Now I have to find the curvature. I have to take one more derivative. Okay. So I have to take the, remember this is defined as the TDS. Okay, which is okay. So I have to take the TDX divided by the SDX, the usual story. Okay, that takes a bit of computation, so I'll just tell you the answer so I don't run out of time. So I'll do it over here. And we get that the curvature, the TDS, is given by the TDS, which is the curvature vector, is given by 0, 0, and then I'll write the leftover term. It's f sub xx plus 2 f sub xy dy dx. Remember, dy dx is just tangent theta. Plus f sub yy, well, dy dx squared all divided by secant squared theta. Okay. This has a nice formula, by the way. This is just cosine theta minus sine theta times f sub xx, f sub xy, f sub xy, f sub yy, 2 by 2 matrix, times cosine theta minus sine theta. So far, so good. We'll save this formula. We use it again. So what does it say? It's very important. I've derived that if I want to know the curvature vector in the direction of the velocity of a vector v, it's v transpose, because this was the original vector v. So this is v transpose, here's v. So it's v transpose. This matrix was the Hessian. Of f. So Hessian of f times v. So beautiful formula that says if you want to know the curvature in a direction v, you hit it from the left by v transpose, you hit it from the right by v, you take the Hessian in the other direction. And this will give you, this has to be evaluated at the point P, and that gives us the curvature. Now the formula is based on one proviso. Okay? Remember that I put the tangent plane here, flat. So that means the first derivatives were 0 at P. At P. So the general formula won't be as pretty. But do we really care? Okay. And because this one is exceptionally useful. It just says, okay, if you want to do the computation, put the tangent plane at P, and now you know the curvature vector. Okay, so didn't finish my computation though. So I know the curvature. So I know the curvature. Here it was. Okay. So I can write it out again, and then I'll finish. So I promised to do the computation. So let's erase here. So I know the curvature vector as a function of theta. Here it is. So write it out. As a quadratic form, it's fxx cosine squared theta minus, because of the way I chose things, f sub yy sine theta cosine theta plus f sub yy sine squared theta. Remember, the f's are all evaluated at the point P, because that's where I'm doing the computation to find the curvature. And now what was the, so this is the magnitude, so plus or minus the scalar curvature. Okay? And now what did I say? I want to find the principal curvatures, which means I have to differentiate with respect to theta. So I differentiate with respect to theta, just as in calculus exercise, and set it equal to 0 to find the extremum, max and min. Okay, you do that, you find right, this one gives a 2 cosine sine, and then sine cosine, etc. So let me finish up, because people have to go. So it's 2 cosine theta sine theta f sub yy minus f sub xx plus 2f of xy sine squared theta minus cosine squared theta. Okay. Then you remember the double angle formulas. So this becomes sine 2 theta. This becomes minus cosine 2 theta. So it says the kappa d theta equals 0 when tangent 2 theta equals 2 f of xy f sub yy minus f sub xx. And why does, now we answer the question. It's tangent 2 theta. So if I draw the graph of tangent, everybody knows the graph of tangent. But what's the graph of tangent 2 theta? It's minus pi over 4 plus pi over 4 and then 3 pi over 4 asymptotes again. So given the right-hand side, find the left-hand side. That means given the right-hand side, make a horizontal line and find the left-hand side. So what are the solutions? Here's one, here's the other, and then all the others, you just add on. Won't make any difference. Okay, it'll just change the direction from pi by an amount. It'll just change the direction. So the two that you'll get, is this one, and that difference, if I didn't make a mistake, you can see here in the extreme case, the distance is precisely pi over 2. So that's why proof that the two directions are orthogonal. Okay. Good place to stop? Okay. Any questions? Everybody's happy? Okay. See you tomorrow, 10 o'clock.